completely new materials properties. And so I want to be able to do this in a very on-demand way so that whatever properties I want to have in a material, I can just create them in whatever material I have. It's kind of the dream. All right, so what do we actually do in the lab? Is we make measurements of different things. So almost everything we do involves shining a laser pulse onto something, okay? And so in these different cartoons, I've got different examples of the kind of measurements that we make. So first of all, we can take some material, which is shown here as this kind of like lattice of atoms. We can shine an intense laser pulse on it, and that atom or that material can change the properties of the light that are emitted by the material, okay, or that are transmitted through the material, right? And what we can do is we can characterize the emitted light and try to understand what that means about the properties of the material. A second thing we can do is we can measure the electrons that are emitted by a material. So for example, from, back in the early 1900s, Albert Einstein showed that if you shine high frequency light onto a material, that electrons come off. And if we can measure the properties of those electrons, for example, we can measure how much energy, how fast the electrons are moving and in what direction they go, then we can use that information to trace back what the electrons were doing when the laser pulse hit them in the material. We can create little circuits. So this is a very simple kind of little circuit. Basically, we have a piece of silicon dioxide glass and we put a couple of electrodes on it and connect them to a current measurement device. Then we shine a laser pulse into that silicon dioxide glass. We can cause that insulator to become conducting for a fraction of a second, right? And we can measure the current that travels through the silicon dioxide. This is kind of our first step towards actually making those kind of devices that we're talking about. These are, really just understanding the basic properties of a simple electronic circuit based on these materials. And the last thing is the reflected light. So just like I can shine a laser pulse onto a material and measure the light that passes through, I can also shine an intense laser pulse onto a material and measure the light that gets reflected from it. And for different materials, one or a few of these might be the best modality for an experiment. And so we kind of try to choose the experiment to fit what we want to do. The dream is that we can kind of combine these tools to really understand what is going on to the electrons in a material when it's hit by this laser pulse, and use those properties in some kind of, a more complicated circuit than what I've shown here on the left to create some kind of a device that basically we can use we shine a laser pulse on it and we can control the properties of the, let's say, the current that comes out. So in this case, we see a bunch of random electrons passing through, let's say, a wire that's connected to this device. And after the laser hits on it, we've made those electrons all bunch up in a certain desirable way. All right, so who are the people who actually do this work? And yeah, so this is my group. So I work in what's called the Laboratory for Ultrafast Metrology and Attoscience in Solids. This is me, I'm Mike Cheney. This is our website. And this is a old group photo since we haven't taken a new photo in probably about 2 years now. And so a number of these people have since left. We've got a couple of new members in the group, but I like to show this picture because it gives a good sense about what kind of possibilities there are for people. So my first two graduate students were Shima Golamirze and John Bitar. John is now at Berkeley. Shima is now at the University of Ottawa. They're both working for the people who are the absolute leaders in ultrafast science in the world. Three undergraduate students. So I've got Aaron Kreitz, it was an undergraduate student in the group. Jonathan Nesper was an undergraduate student in the group, and Marc Etienne was an undergraduate student in the group. Aaron is now a PhD student in physics at NC State. Jonathan is now a PhD student in physics at UCF, and Mark is now a PhD student in aerospace engineering at UCF. And then I have this is a postdoc who was in my group who's now at Ohio State. Our work is funded from a number of agencies, so you can get a sense of what are the applications of our work. So we're funded by the Air Force, we're funded by energy, so things like renewable energy definitely have a place to play or hopefully we have a place to play in that field as well. So with that, I would be happy to answer any questions about my research or the group.
Wonderful. Thanks a lot, Mike.
Mm-hmm.
All right, so the floor is open for some questions on what Professor Cheney presented. Any questions from the students?
If they have any questions about the program as well, is this the time for them to ask?
There's one more presentation we
Okay,
have for
and at
them
the end.
as well.
Okay, gotcha.
Yeah, I'm also
Not
happy to
bad.
answer questions by email. So if you've got any questions and you want to just shoot me an email, that might be a kind of lower stress environment to ask a question.
And I just send the link for our website as well if they're interested in looking at that.
There's a question in the chat. Is this program a co-op? And what software do you use for your research? 2 questions.
I would let Professor Kondakar reply if this program can be called a co-op or not. Saiful?
What does co-op means? If you can say what you
Ellie,
mean
do
by
you want to
co-op.
elaborate your question? You can type or unmute your microphone, Ellie.
Hello, yeah. I'm just asking if it's kind of like it happens during the year. So let's say during your school, is it, let's say after your classes and then you go to research, or is it during particular weekends? I'm not really sure what days or how this particularly works.
So basically you work as a research intern and you work, first of all, you need to be interested in the research areas that we are talking, because we have a specific research areas that are funded. And then if you apply and you get selected, you are expected to spend 15 to 20 hours in the lab per week. And that would involve, you'll be co-mentored by a graduate student. And so it is dependent upon the arrangement of the PI and the graduate student when you are going to come based on your schedule. But most of our students come, for example, my own student comes 3 to 4 times a week after the classes, or depending upon if the class is in 2:30, then he comes in the morning and spend 4 hours, 5 hours. Or if it is if the classes are in the morning, he comes in the afternoon. If the classes are both morning and afternoon, he doesn't come on that day. So it's an arrangement that he makes with the graduate student who works closely with him. And so, yeah, the main point is that you have to be driven. I think driven is a word that I think needs. We would like you to enjoy the research. We'll make sure that you get you belong to the group. We have a cohort meetings with University of Washington. So it's an opportunity. If you want it to be, you just have to have the desire to be somebody. In materials research, you are looking for opportunities to be somebody, and then we will provide those opportunities to you, and you will make the most of those opportunities. That's what the position is. And also, I'm not sure Professor Banerjee mentioned this particular center is about training underrepresented minority students in materials research. So, and people who were underprivileged, did not have a shot, and yeah, so we are looking for those kind of people.
Okay.
And there's just some clarification on co-op that it generally refers to work experience that can be added to your resume before graduation. And then we had a second question: what software do you use for your research?
So I'll take the first question, and of course you can put that on your resume that you were part of the center and that you went through a research internship, is what we'd like to call it. But again, if you refer back to some of my earlier slides, the vision we want to provide you and the opportunities that Professor Kondakar is mentioning is for you to take this as a launching pad for you to get to graduate school and beyond. And that time horizon is a longer, more strategic time horizon. And we feel, and so does most of the federal granting federal funding institutions feel this way, is that the longer you spend in acquiring higher and higher degrees, the more are your chances of career and life success. And so our ultimate goal, and that's how we typically screen students, is for students who have a desire and who want to grab this opportunity by their horns and move towards acquiring a higher degree beyond undergraduates.
So I want to emphasize again, this is not a job and this is not a work. So that's not a job experience and this is not a work experience. Okay, this is a research experience, and research, you will be trained, you will be learning, and then you will be contributing. So it's not like you come and wash some dishes and then leave, like a job. This is not those kind of work. It is not a job. Or
you have to be invested in this,
yeah,
both mentally and physically. So we are calling on the most
it's a research
motivated
experience, not work experience.
Okay. There was another question that said, what software do you use for your research? So Mike, would you like to answer that?
Yeah, sure. So in my lab, we mainly use Labview software. This is a common software that's used for automation of different processes. So for example, if our lab our experiment might have multiple moving parts, and so we want to make sure that those move in tandem with each other, and we can do that with Labview. We can also collect data with the Labview software. So for example, using a camera to collect images, or using an electronic circuit to collect currents. And so we use that to automate a lot of our experiments. In my lab, we build experiments on the table. We tend not to buy a lot of equipment. Everything is built by hands by the people working on it. But when you're collecting the data, a lot of that process can be automated. And so if you're proficient in, if you're interested in learning that kind of coding, then I think that can also be a great opportunity for you.
Yeah, so I wanted to add on is that, yeah, we also use Labview for data acquisition. So as Professor Chinni mentioned, that Labview is to acquire the data, right? And then after you acquire the data, you will plot them. And for that, we will use, what is this called? Origin. We use Origin to analyze the data, to plot them, and then you will use PowerPoint to make presentations, and so and then you will write report. So it's a lot of different things. So for presentation, you will use PowerPoint. For writing report, you will use Microsoft Word or something along that line.
Okay, I think in the interest of time, we should move. Oh, go ahead.
So we also use Labview. So something important, SpaceX is using Labview a lot for their rockets. So this is very useful. And yeah, you have the chance to learn it probably in each of those labs.
Yeah. Again, we don't expect you to know these skills. The point is you come to our lab, we train you, and we build you your skill sets in a way that helps you apply to these top graduate school programs in the country and the nation. Right. Okay, in the interest of time, we should move on. We have about 15 minutes left, and I have Professor Vaida waiting, and he will talk to you about his research program as well. So Mihai, it's all yours.
Can you see my screen?
Yes, we can.
Okay, perfect. So my name is Mihai Vaida. I'm a faculty in the physics department, and yeah, I will say a few words about my research. I will not go into many details. So what you see here, like on this slide written, it's XUV ultrafast spectroscopy on 2D nanostructure material. So basically, I will just like use some other words to explain what I do. So the main goal is of our laboratory and of our research is to create novel catalytic and photocatalytic materials that can can be used to produce fuels from renewable sources. So for instance, when you come to UCF, you are driving your car, and while you are doing this, in your engine, you are burning gasoline. So you are oxidizing gasoline in oxygen atmosphere. And the products of this reaction, there are many products actually, but after the car catalyst, what it comes out of your car, it's mainly CO2 and water. So what we want to do is to create materials that can convert CO2 and water back into fuels. Okay, so this is what we want to do in our laboratory. And basically, this is what green plants are doing. So if you're looking outside, you see a lot of photocatalysts. They are like taking CO2 from air, water from soil or air, and using the sunlight, they convert to hydrocarbons, which are the plants by themselves. But of course, so the plants are if you want fuels, but they are not the right fuels if you want to drive your car or if you want to fuel a rocket or so on. So we want to produce liquid fuels that we can store, that can be produced using only CO2 and water and the light from the sun. So basically what we do in our laboratory, we create materials, but more than that, we investigate the materials, we investigate the properties, and there is something else that we do. We are using very short laser pulses, and this is what the title of my presentation says, to investigate or to look at the atoms and molecules during chemical reactions. So to take real-time movies of atoms and molecules during chemical reactions. We can also look at the electron transfers, like the charge carrier dynamics, but most of the experiments is to look at to take movies of atoms and molecules during chemical reactions. So I'll just show some slides from my laboratory. So we are using very short laser pulses, as Professor Chini said, and they are used so if you want, we have a camera that can take pictures. This is the ultra high vacuum chamber that you see right here, in which we do all the experiments. And we have a ultra fast laser that produces those very short flashes of light, and they are used to take pictures of atoms and molecules in real time. Okay, so basically in my laboratory, we'll do surface science, so we create materials, but we also do ultra-fast spectroscopy. So we use both lasers and vacuum stuff. So this is a picture of the setup that I use in my laboratory. You see here a big table. This is used to basically only to produce very short laser pulses of light with very high photon energy. So it's kind of special light. And in this part of the setup, we are creating materials, but we are also taking the movies of the atoms and molecules during chemical reactions. And yeah, these are just different pictures of the setup. This is just to get an idea. We produce photons that have very high energy. So we can go actually up to 100 electron volt in our laboratory. And this is something that we normally use for electron molecular dynamics, so to look at the motions of electrons and atoms. So just a few words about the setup that we use. So all the experiments that we do are inside the vacuum chamber. So as I said, we are making the materials by ourselves. So what we have here, we have various tools for surface preparation characterization. So we have a tool here to clean samples. This is an argon gun, so you cannot wash a sample inside the vacuum. So the only way to clean it is by bombarding the sample with high energy atoms. So we use argon for this. And in that way, you just remove the first layers of the surface or from the surface. And then what we have here, we have some evaporators. They are nothing else than ovens. So we can heat up materials at very, very high temperatures. So for instance, we have here 2 electron beam evaporators. They can melt basically any metal that we know. So we did a lot of experiments with tungsten before. This is the highest melting point metal that we know. The sample is right here. This is attached to a liquid nitrogen cryostat, so it can be cooled down to very, very low temperatures. We can evaporate on the sample, so we can create like films. We can create oxides, sulfides. We can add particles on the surface. And then what we do with the surface, we investigate it. So we have different tools to investigate the structure and composition. So we have here a tool that it's called low energy electron diffraction. This takes images of the crystalline structure of the surface. We also have a tool that is called Auger electron spectroscopy or spectrometer. This can look at the composition. So it can see exactly what type of atoms you have in your sample and how many they are. So you can do quantitative and qualitative spectroscopy. On the other side of the setup, you cannot see it from here, but you can see it in this picture. It's a long tube. This is, can you see my mouse moving on the screen? So this is a time-of-flight spectrometer. This is if you want the photo camera. So the time-of-flight spectrometer with the laser system that it's on the right side, it's nothing else than the camera and the flash that we use to take pictures, real-time pictures that we can put together and get movies of atoms and molecules during chemical reactions. Okay. These are images from inside the chamber where you see different evaporators. You see the time-of-flight spectrometer that I said is the camera, the sample, and something that I need to mention, most of the parts are not commercial. So they were constructed, and most of the parts I constructed with undergraduate students from UCF. So I had like a few students from physics and from the engineering that they construct some of those parts. So this is something that I need to say. So what we do in our laboratory, we create samples. So we can create basically two-dimensional, basically it's just a layer of material that are, therefore we call them two-dimensional, that are highly crystalline materials, and they can be semiconductors or metals, or they can be insulators. And we can look at their composition. So as I said before, you can use Auger electron spectroscopy. So you see some peaks, and these are peaks that are element specific. So for instance, if you see a peak at 60 electron volt, this must be copper, and so on. So they are like peaks that are element specific, so we can identify the composition. And the other tool that I mentioned before, we can look at the crystalline structure. So we can do electron diffraction and we can see those materials. Okay, and we can create, these are just materials that we produced in the last year. So we create a lot of dimensional semiconductors for our research. And we also did heterostructure. So you put two semiconductors on top of each other, and this is nothing else than a solar cell. Okay, so this is also something that we did in our laboratory. Like we put semiconductors on top of each other, and then we are looking at electron dynamics. This is a movie that you see here. So with light, we excite one of the materials. And then because we have this heterostructure, like two semiconductors on top of each other, the visible light excites one, and then there is an electric field built between those two different materials that will separate the electrons, which are the negative charges and the positive charges. And this is basically nothing else than a solar cell or a photovoltaic material. So we can create those kind of photovoltaic materials, and we can also look in real time at the electron migration from one material to another one. Okay, The other thing that we are doing in our laboratory photocatalytic materials. So these are the materials that are used to create fuels from water and CO2. So these are like semiconductors, and on top of the semiconductors, we put metal particles. And we can also look at the motion of electrons, or like the charge injection from the semiconductor to the metal particles in real time. And the goal is to have a very fast charge injection and then a very slow relaxation of the electrons from the particles. And these are like measurements that we can do in real time using very short laser pulses. This is another experiment that we do. We also do simple catalysis. So we produce catalytic materials. And this is something, a new project on which I work right now with Professor Banerjee and Professor Kondaker. So it's like a new project in which we are doing materials, and we are driving chemical reactions, not using light, but using heat. And the last, and probably the most important type of investigations that we do in our laboratory are those in which we are looking at the motion of atoms and molecules during surface chemical reactions. So basically what we do, we dose water and other molecules on the surface, then using not sunlight, but laser pulses that can mimic the sunlight, we excite the photocatalyst, and then charges will migrate from the photocatalyst to the molecules. And then the charges will induce the fragmentation of the molecules. Then you have so-called radicals. So chemists are calling them radicals. These are atoms or molecules that have unpaired electrons, and they are very unhappy until they react. So they are just searching for a partner to react. And they react, and then using a second laser pulse, we are taking pictures of the molecules that are formed in the real time. Okay, so and putting all those pictures together, we can get movies of the chemical reactions. And now I will just jump a few slides. I will not really explain how everything works, but I can show you a slide in the end. And so basically we can get a lot of information about the dynamics and how the atoms and molecules are moving. But this is a new study. We put on surfaces water. So instead of H2O, we put D2O and methyl iodide. This is a molecule that contains carbon, it's not CO2. This is a poisonous molecule. And then using only light, we were able to form methane and methanol. And basically not just to form methane and methanol, but we see very unstable radicals. So these are species that have a very, very short lifetime, and we can basically observe them in real time, how they are formed. And I will stop here. And if you want to learn more about my research, I'm then happy to schedule some extra meetings, or if you want, you can stop by and see my laboratory and we can discuss more about this.
Thank you, Mihai. I just wanted to say something is like, so the research that you learned, I'm sure that, most of it, you did not get it. That's okay. What we are looking for is that this is an opportunity for students to learn and discover, okay, at the forefront of science and technology. So this gives you an opportunity to discover. So therefore, if you are excited about discovering new knowledge, new science, new technology, okay, this is what these opportunities are for. And so what are you going to get in return? Well, you will be a leader. You could be a professor, you could be a leader, a manager in the industry, okay? Obviously, this research you're going to start, and we hope that, that you would continue that to the graduate school, which will be completely paid, and that after the graduate school, you are going to make a lot of money, that we are going to alleviate, your family, you will be an example to your community, that show, what can be done by research and by discovery, so that you'll be a role model for other people to follow. Okay.
Thank you all for the presentations and information. We're right at 2 o'clock, so we want to respect everyone's time, but if there are any questions, we'll allow for a few more minutes. Students, if you have any questions for the respective faculty and their respective research.
I would like just to answer a question. So I was asked like on chat if you need a lot of background for my experiments. No, you don't need. I did a lot of work with, actually I did a lot of work with a high school student. He constructed parts of my setup. And I also did a lot of work with freshman students. So like students, they did not take physics 1 and 2. I mean, they start to take physics 1 when they join my laboratory. So the only thing you need, it's just a lot of motivation. Okay, so we are here to teach you and to train you. The only thing you need to bring is motivation, and everything will be fine. So you don't need to know much before you join the lab.
Yeah, so Eli, if you didn't see, or Ellie, the answer to your question, you can email the professors individually to schedule times to visit their labs. And Professor Vadi is in Research 1. You can contact him via email. Professor Chini is in PRB, same there. You can contact him via, or PSB. You can contact him via email as well. And all of the faculty, you may contact them via email.
And you can also visit the other professor's lab that did not present today. That's also okay.
In the PRIM website, again, is
Yes.
here in the chat, so you guys can refer to
Yeah.
that for additional information.
Right.
Well, thank you so much for your time. Thanks, Sherry, as
coming.
well.
Thank you all.
Thanks, Jimmy. Thank you.
Thank you,
Bye.
students, for attending. Be sure to reach out regarding your research interest. And Parab, I'll send you the recording once I receive it.
All right. Thanks.
Okay.
Sounds
Thanks,
good.
everyone. Have a
Take
great
care.
day.
Bye-bye. Thanks, Jimmy. Bye.